Alright, so now we will have more factor tricks. Factorials, they are interesting, and we saw them in counting before as the answers to like many counting problems and also involved in the answers of many counting problems. And they're interesting as they're defined as the products of many numbers. There's one specific trick for it, but otherwise the same things work all the time. So find the sum of the numbers of 9 factorial. Find the largest power of 3 that divides it. The specific trick is to do with the last question, because some of the factors of 9 factorial, well, you have no choice to just factorize. Since factorials are every integer less than some number multiplied, we can just directly look for the powers of what we're dividing, of what we're looking for. So if we're looking for the largest power of a composite number, we just look at the largest prime factor because that will be the limiting one that will limit how many times that power, how many powers divided. Okay, so for what this trick is that we want to count all the powers of 3 dividing numbers from 1 to 3 to 9 and add them up, right? So first we only have to do this up to the largest power of 3. So how many multiples of 3 are there? That's the floor of 9 divided by 3. Now this is an integer, but we have to use the floor function just in case we have something like 8 factorial. And then we have the floor of 9 divided by 9, and we could keep going and add the floor of 9 divided by 27 and infinitely on, but like since we just see that it stops as 9 and as 9 and all the other terms will be 0, there's really no need to. Anyways, so why does this work? What does this represent? This counts the multiples of 3. 3, 6, 9. It accounts, not only that, it accounts for 1 power of 3 from all of them. So it 1 power of 3 and 3, 1 power of 3 and 6 is 1 power of 3 and 9. Now that this is important because it only counts 1 from 9 and not another one, which comes down to this one here. This 9 over 9 finds a number that is divisible, find a number of numbers divisible by 3 squared and accounts for 1 more power of 3. So this is where the 9's second power of 3 is accounted for. If we had multiples of 27, 81, it would be the same thing. We account for, since every number, if we have like a number that's multiple of 3 to the n, this will be accounted for n times in the floor of k over 3 once, k over 3 squared once, up to dot 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 k over 3 to the n once. So okay, I know this might be a bit hard to understand, but this is why this like formula works, since we kind of like level up counting the powers of 3, adding them on each time. And of course, this formula on 9 factorial would give 4 powers. This is correct. 3 has 1, 6 has 1, 9 is 2. Now that was easy to count using just like mental math, even since like we know what gives powers of 3. However, if we want to find for something that divides like something like 99, then this is a lot more in handy. So actually, I would like you to try this and tell me the answer. And yeah, just privately chat me the answer once you've got it. All right, I see someone's got the right answer. Let's go over this. Remember, we only need to go up to the largest power of 3 that is less than 99. In this case, it would have been what? 3 to the power of 4, right? So this would be 499 over 3, 99 over 9. Plus 4, 81. It says 33, 11, 3, 1. 44, 4, 48. Nice. So yeah, 48 is indeed the right number. 48 powers of 3 in 99 factorial. That's a lot. Very hard to do by doing mental math, not following a similar process. So yeah. Okay, so we have some more in-class problems. What's the LCM of 6 factorial and 600? And what are the product and sum of factors of 126? Is it abundant or deficient? Now we'll have you work on these. Okay, so LCM of 6 factorial and 600. 6 factorial is 720. 600, well, yeah. So if you're experienced, you can kind of just pull out 6 times 120, 5 times 120 here. And notice that this implies that 120 would be the greatest common factor, since if you divide the numbers by the greatest common factor, there should be no more greatest common factor among the remaining stuff. So the greatest common factor can also be equivalently defined as a number when you divide all the numbers by the GCF of all the remaining numbers are relatively prime collectively with each other. So knowing this, the LCM would be 6, since 120 divides both of them, it would be 6 times 5 times 120, since we don't want to double count this GCF. So it'd be 30 times 120 is equal to 3600. Now, what I did here is actually like closer to the Venn diagram thing. And so yeah, like if you draw the diagram, sorry, this is too small, but 120 would go here, 6 here, and 5 there, thus making it clear that the answer is 30 times 120 or 3600. Okay, so now what's the product and sum of the factors of 126? I'm not seeing any answers for this yet, so I'll give you some more time to work on it. Private chat me your answer once you're done. Okay, so I see someone's got it. So the sum of factors of 126. 2 times 3 squared times 7 if you prime factorize. So the answer, the sum of the factors will be 3 times 1 plus 3 squared times 8, 24 times 13, which is 312. So since 312 is bigger than 2 times 126, which is 252, this number is abundant. Now I hope that this should have been like pretty clear and straightforward. So yeah. And with that, class is over. We will assign a practice AMC and possibly some more homework problems involving this topic. But I would say since the AMC is drawing closer and closer, you want to do that as well. And we will cover again more number theory next class. So yeah, class is over and you're free to leave.